So I hope you caught how much example 1 really was review. Every single thing in here was stuff that was already covered in chapter 4. The only thing that was new was this little bit right down here where we took the log of both sides. That's it. Every single thing up to that, other than that, can be done without chapter 5 stuff. All right, and that's the way this problem is going to be as well, more review. So let P be the percentage of U.S. households with digital video recorders, DVRs, such as TiVo, at T years since 2000. So this is the percentage of U.S. households with DVRs. So what we're going to have to do is grab a calculator and see stat, edit, and let's see, clear out the olds. We don't need that anymore. Go over here, up and clear. All right, I'm going to type in the new, but remember this is years since 2000. So that's actually 1, 2, 3, 4, 5. And then over here, 1, 2, 4, 6, 10. All right, so then we want to use a graphing calculator to draw a scattergram of this. Okay, so remember how to do that. Go to y equals, clear out your old equations. You don't need any of that anymore. Go up to plot 1 and press enter so that it's dark. So when you move away from it, it's dark. It's called highlighting. If it's highlighted, then it's on. And then do zoom 9. And there we go. Cool. All right, so let me take a picture of that, put it in here. And then the question is that a better model for linear or exponential? All right, so let's see here. That would be a better exponential model because the points have a curve to them. Do you see how they increase a little bit and then a little bit more and then increase even more and then increase even more? It's not that it's going up, it's the fact that every time it goes up by a little bit more than last time, especially at the end right here. It's really starting to arc. So exponential because the points form a curve, which seems kind of like a silly thing, but it's actually really important to you guys for one of your projects. Being able to look at a scattergram and make a decision like that. Oops, hold on one second. There we go. All right, so now let's find an equation for f using our calculators. So we're going to go to the calculator. We already have all the points in there, so just go to stat, calculate. 0, remember, is exponential regression. And what the hey, I'm going to store it. So I'm going to go to variables, y variables, 1 and 1. Enter. And there we go. So now I've got the equation and it's stored. So let me see here. F of t is equal to 0.62103 times 1.76894 to the t. I probably did a few too many decimal places on that. But that's all right. You're better off with more decimal places than less. Right? And I used exponential regression. Right? Whenever you're given a whole table of points, use all of them. Right? So use exponential regression. All right, now what was the coefficient of our model and what does it mean? So that would be a is equal to 0.62103. Right, 621. Let's simplify our lives a little bit. All right, so it was 0.621. Now what does it mean? It means that in the starting year, which was in it was 2000, right? 2000 was the starter year. So in 2000, the model estimates that there were, that about 0.621% of U.S. households had DVRs. Much smaller than it is nowadays, right? All right. What is the base of our model and what does it mean? Good question. The base would be 1.769 or so. So base is 1.769. I'm rounding a bit, but that's fine. Okay. So now what does it mean? Okay. Chapter 4, remember, it's not, okay. We know it's increasing. I mean, for one thing, you can see it's going up. So every year, oops, I don't know why I unbolded that. the percent of U.S. households that have DVRs is increasing, right, going up, and you can tell it's going up because your base B is greater than 1. Remember, 1 is the flat line level. If nothing was happening, it'd be B base is equal to 1. If it's over 1, it means you're increasing. If it's below 1, it means you're decreasing. Now, here's where students get all messed up. They want to say it's increasing by multiplying by 1.7 or something like that, and it's a percentage increase. So what you want to do is you want to take B away from 1, right? Because if 1 is your flat line level, then you want to take B away from 1 to figure that out. So if you take 1.769, take away 1, you're going to get 0.769, which is 76.9%. That's your rate of increase right there, not 0.769, or excuse me, not 1.769, which is what everybody always wants to say. So you say every year, the percent of households that have DVRs is increasing by 76.9%. You always take it away from 1 or take 1 away from it if it's a decreasing problem, because 1 is your flat line level. We learned all of that in Chapter 4 repeatedly, so it's back. All right, now find f of 7, and what does it mean? Well, f of 7 would be equal to, what were these numbers? Oh, okay. 0.621 times 1.769 to the 7. Oh, I think this is actually the next page. Yep, it is. All right, sorry about that. I fit all of these into this page. Okay, so 1.769 to the 7. And of course, I'm going to make my calculator do that. That's, not pretty. So, and if you have it already in there, like I stored it, so I could just go to the table and see what it is at 7. It's 33.6. 33.7, honestly. 33.66, I believe. Something like that. Or you could type it, one way or another, you can get that it's 33.66. And then the question is, what does it mean? Well, in 2007, because our starter year was 2000, so 2007, about 33.7% of U.S. households, well, I should say the model predicts, the model estimated because it's in the past. The model estimates that about 33.7% of U.S. households had DVRs. It's getting there. I mean, we have a lot of DVRs right now. I mean, very few people have VHS machines anymore and stuff like that. All right, find f inverse of 100 by hand. What does it mean? Well, tricky. Okay, so remember, we learned in section 5.1 that the inverse, there's two things you could do. One, you could try to find the inverse function, but the only method we ever learned for finding inverse functions, I'll just go back here. We learned two things. We learned how to find the inverse of a linear model. This was linear stuff. Remember, that was actually the title of the section. Inverses of linear functions. So in both that page and this page right here, these are linear models because x is to the 1 power. And then the other thing we learned was in 5.2, we learned that logarithms and exponentials are inverses of each other right here. That's all we've learned. But we haven't learned how to actually find an inverse function for anything other than these extremely simple ones right here and then the linear stuff. But we don't know how to find the linear or the inverse function of something as ugly as what we were just looking at. This model, oops, there it is. This model that we have, we don't know how to find the inverse of something like that. So we're not going to. Remember that an inverse function, when you look at the parentheses inside a regular function, like the 7 here, that 7 means that, here, let me put it this way. It means that t is equal to 7, and then where they're asking you, 7, and then they're asking you, what was this? I think it was p, percentage. They're asking you for the percentage. They're saying p, which is equal to f of t, is equal to what? Right? That's what you're doing when you do this. So when you do the inverse function, it's the opposite. Right? When I look at that 100, I'm not saying that t is equal to 100. Because it's the inverse function, it's p is equal to 100. And they're asking you for t, which is equal to f inverse of p, right, is equal to what? So what you're going to do is you're going to set your equation equal to 100. So you're going to say 0.621 times 1.769 to the t is equal to 100. You're going to set it equal to 100. Now look at you. You've got a variable in your exponent. You see that? There's only one way to solve this, and it involves logarithms. But you can't do the logarithm part first until you've gotten rid of the 0.621. 0.621 is no good to you. So you put 0.621 in the denominator. This is going to cancel over here. Not cancel, divide. Divide by into 1, right? Okay, so you get 1.769 to the t is equal to roughly, let's see, 100. Let me quit and get out of here. 100 over 0.621. 100 over 0.621. Enter. Is about 161.03. 031, if you will. All right, and then I'm going to take the log of both sides because I need to get t out of that exponent. So I'm going to take the log of this side. Oh, I better do it as a separate list. Hold on one sec. All right, so if I put it here, and then I'm going to take the log of this whole side over here, and I do that for a very specific reason. We'll talk about it in a second. And the log of this whole side over here. Okay, now I did it because then I can bring my t down in front. So it's t log of 1.769 is about equal to the log of this guy, right? Taking the logarithm allows you to bring their variable down in front using the power property. That's the whole reason you do it, right? That's why they're inverses of each other, is that that property holds. All right, so then we're going to take both sides and divide it by the log of 1.769 because we need to get it the heck out of there. And of course, we're going to make a calculator do this. This is not something you're going to find by hand or anything. All right, so then you find what this divides away, because whatever this number is, it's going to go. There we go. So we have t is about, and then we need to find what this number is. So I'm going to take the log of that answer, which is 161 and change, close parentheses, be sure to close those parentheses, divided by the log of 1.769. Enter. And it's 8.9. All right, so now we found it by hand. Now you might be thinking to yourself, well, Lana, how would I have found it with my calculator? Good question. If you have your equation, the original equation, 0.621, blah, 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 in there, then all you would do is put 100 down here and make sure that your window is big enough that you can actually see. Oops, I don't know why I did that. Window. There we go. You need to make sure your y is big enough that you can get to the hundreds. So like, how about 120 here for your y max? 0 for your y min, and then let's make this go from 0 to, I don't know, 0 to, well, we think it's 8.9, so try like 12. Let's just see that. And then you'd have your equation, your exponential equation coming through like that. There's the original 5 dots we made this equation from. And then there it's come in and across, and you would just do calculate, intersect, enter, 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 and it will find it right there. Right? And that's always good to be able to double check yourself. So you can always double check yourself with a calculator, and it should back up what you already found. Now let me type up the meaning. Hold on one sec. There we go. What we just found was when, because we solved for time, which was, I rounded it to the nearest year, so 2009, that would be when the model predicted that 100%, because we found it for F inverse of 100, 100% of U.S. households should have had DVRs by 2009 according to the model. Of course, that's not actually true. It didn't work out, but that's what it claimed, right? Matter of fact, I threw in the should have had, right? All right, we are all done with that example. So I noticed the F inverse, we never actually found the inverse function, but it didn't matter. All that means that we set it equal to 100. You can still totally do that. And that might show up on your final. Hint, hint, hint. All right, I'll see you back here for the last example.